Hi, physics folks. Let's look at the key, or make a key, for the practice test you guys got for your motion unit. Number 1, during the day while he finds waste, compacts it into cubes, builds it into structures like the ones pictured above. He does it at a rate of 140 inches per day. How many meters per year is that? So this is a unit conversion question. So the way I like to start these problems is I like to say, okay, well, what am I really looking for? I'm looking for meters per year. Okay, so that's going to equal 144, inches per day if I do some converting, okay? So obviously this doesn't equal this exactly. I have to put in some conversion factors. So what should I put in? Well, I have day on the bottom. I need year on the bottom, so I'm going to start with that. Just why not? I know that there are 365, and this is a multiplication sign, by the way, 365 days per year. So by doing that, if I were to multiply this across just as it is now, I would see that the days are going to cancel. Awesome. So now I have year on the bottom. I'm good. So am I done? No, because right now my unit is inches per year. So I need to make inches go to meters. Okay, so I need somehow to put meters on the bottom to make meters. Sorry, do I have that already? Meter to feet. No, I don't have a direct thing for that. So what should I do instead? I'm going to start with inches and make inches go away. So I'm going to put inches on the bottom here. I know that there are 12 inches in 1 foot. Okay, so that means inches go away. And then I'm not done yet because right now I have feet per year. I need feet to go away. So I'm going to put 3.3 feet. Oh, look, that's 1 meter. So then that means that my feet go away. Foot, feet, done. Oh, why did I write meet when that should be meter? There we go. Awesome. Okay, so what do I have left for my units? I have year on the bottom. That's what I want. I have on top, I have meter. That's also what I want. So now if I get rid of the stuff that is kind of cluttering this and just make this a math problem, what does this become? This becomes, if I want meters, again, meters per year, now I have 144, and I'm actually just going to extend this line to make it easier. 144 times 365 times 1 meter. That's what I want. Awesome. Then on the bottom I have 1 times 1 times 12 times 3.3. That's a decimal. Okay, feet. Nope, let's see where it was. It was year. That's what I have left now. So now I'm going to multiply this out to make it a little bit easier. If you were just to multiply across, if you did 144 times 365 divided by 12 times 3.3, if you don't put in parentheses, you're not going to get the right answer. So I'm going to do it step by step. So 144 times 365 times 1 times 1. I don't actually have to do that, but I will. Okay, so that's going to equal 52560 meters over 12 times 3.3, 39.6 years. So now I know I'm going to divide this big number by that big number. So I'm going to put 52560 divided by 39.6, 1,327.27 repeating. I'm just going to use 1 decimal, and so I'm going to get 1,327.3 meters per year. And there's your answer. Boom. Hopefully that made sense. Let's go on to the next one. Wally and Eve are dancing in space. Okay, so we know that Wally is moving at 4 meters per second, and Eve is moving at 6 meters per second. If they are 15 meters apart and she is chasing him, how long will it take Eve to catch up to Wally? Well, so this is a closing speed problem. So E is behind W, okay? And they are 15 meters apart. Meters per second. Oops, sorry, this is just meters. They're 15 meters apart. we know that she is moving at 6 meters per second, and he is moving at 4 meters per second. So the first question is, if you're chasing someone and you're faster than they are, will you ever catch them? Yes. So this is a plausible problem. You will eventually catch them. And the second thing is, if you're moving in the same direction as someone, your closing speed is basically for every second, how many meters do you gain on them? So for every second, she moves 6 meters, he only moves 4 meters. So we're going to subtract them. It'll be 6 meters per second minus 4 meters per second. So the closing speed is 2 meters per second. That's not our answer. That's just the speed that we're going to take into account when we're figuring out what to do next, okay? So I have a speed. My closing speed is 2 meters per second. I'm going to use that to figure out the time, okay? I know that speed is distance over time. I want time, so I'm going to go ahead and manipulate this equation to get that in terms of time. I'm going to multiply both sides by time, or cross multiply if that's what you're used to, and you end up with speed time. So speed times time equals distance. I'm going to then manipulate this again to divide both sides by speed, and you end up with time equals distance over speed. And in this case, it's the closing speed. So I'm going to plug in my numbers. I get that time is the distance, 15 meters, divided by the closing speed, which is 2 meters per second. And when I divide this, you end up with 7.5 meters per, no, not meters, hello. It's just seconds, because you got to think, what am I looking for? I'm looking for time. That's seconds. 7.5 seconds. Done. All right. Wally turns around and propels himself towards Eve at the same velocity. How long will it take for them to meet if they start 10 meters apart? Okay, so Eva is moving this way. Wally is now moving this way. She's still moving at 6 meters per second. He's still moving at 4 meters per second. And they are now 10 meters apart. So how long does it take to get to each other? So if you're moving towards somebody, your closing speed is added because you're both adding the same distance as you move towards each other, okay? Well, you're adding velocities as you move towards each other. So the closing speed in this case is going to be 6 meters per second plus 4 meters per second, 10 meters per second. So you now, the same thing, so how long will it take? Well, we figured out above that time is distance over speed. So we can just plug in time is 10 meters over 10 meters per second, which is 1 second. Now, this may look nice and intuitive, but if you don't show your work, you're not going to get all your credit. So please make sure you show all of your work when doing this problem. Even if it seems tedious, it's very important. Show all your work. Thank you. Let's move on to the next one. People in the picture are moving forward at 3 meters per second with respect to the spaceship. The spaceship is moving the same direction in 3. Let me get a bunch of different colored pens. Let's do this thing. All right. Here we go. So this is where your 4-color pen comes in handy. Make sure you have that for the test. How about a red? Okay. How about a green also? All right, so let's talk about with respect to a nearby star. So let's say this is the with respect to star. Okay, so we know that the spaceship, let's make sure, okay, so the people are on the spaceship at 3, and they're moving at 3 meters per second just with respect to the spaceship. The spaceship is moving the same direction at 350 meters per second. So I'm going to do that one first because the people are on the spaceship, so we need to take that into account. So this is going to be the ship, and it's moving at 350 meters per second. So this is with respect, this line now is with respect to spaceship. The people are on the spaceship, so they're going to be given, their speed's going to go on top of this, and it's much slower. It's 3 meters per second, and this is with respect to people. Wally is between the people moving forward at 2 meters per second with respect to the ship, which means he is with respect to ship, so here, he'll be here. Boop, 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 boop. This is with respect to WALL-E. He's moving 2 meters per second. Awesome. What is WALL-E's speed with respect to the people? So not caring about the spaceship at all. We're looking at with respect to the people. WALL-E's actually, if they were moving, they basically are passing him, which means we know he's moving slower, but to them it looks like he falls behind. So it would be his speed, the wrong color, let's go back. So his speed, 2 meters per second, minus their speed, which is 3 meters per second. And so it looks like he's moving -1 meters per second with respect to the people. Important. Okay. What is WALL-E's speed with respect to the nearby star? So now we're going back and we're saying, well, I want to go from WALL-E to the star. Okay. So it would be this plus this. We're moving in the same direction. And so we're going to add them. Because it's with respect to the same thing. Over here, we're looking at 2 different with respect to's, so we would subtract. So in this case, it's going to be the ship is moving 350 meters per second with respect to the star. WALL-E is moving 2 meters per second with respect to the star. So he is moving 352 meters per second with respect to the star. And that's the answer. All right. Cockroach. Let's look at cockroach science. He falls off a vertical tower of garbage at 5 meters per second. The tower is so tall that it takes him 10 seconds to fall and hit the ground. So I like to draw pictures. Here is the tower. Okay, how far from the base of the tower does he land? We know that the time is going to be 10 seconds. Okay, we know that he runs off this way. Oh, at 5 meters per second. We know that really we don't care how high this thing is. We want to know how far can he move in 10 seconds. It doesn't matter. We kind of saw in one of our labs that it doesn't matter how high something falls off of something. It only matters how far in one direction it keeps going. Okay, so we're looking for this distance. Okay, so this is our x. Okay, and it's a distance. So, we have, if you may be asking, how do I even solve this problem? Well, I have a speed, I have a time, and I want to know how far, and I know far is distance. So I can look at my equation, speed equals distance over time, and I can solve for distance this time. So I'm going to multiply both sides by time, and I end up with speed. Speed times time equals distance. And now I can plug in. Okay, so I know my speed is 5 meters per second. I know my time is 10 seconds. And so then my distance, you would just multiply them. So your distance is 50 meters. Boom, done. Awesome. Hal likes to write on WALL-E. Oh, if. So here's what my very scientific WALL-E. Boom. Okay. If, here we go. If Hal jumps straight up while WALL-E is moving, where does he land? Does he land on WALL-E? Does he land behind WALL-E? Does he get squished? Give an answer, an explanation, and evidence. So this is like the lab we did with the ballistics cart, where we shot something up in the air, but since this thing was also moving, the ball already had a speed to it when it was shot up in the air. So it lands in the exact same place, okay? So the answer is he lands on WALL-E. Lands on WALL-E. Because he was already moving at the same speed as WALL-E. At WALL-E's speed. When he was thrown in the air. When he jumped in the air. So assuming no air resistance or weird stuff or anything, which we don't, we figure everything is nice and perfect in this level of this class. When you jump up in the air, you're going to land on whatever it was that you were already moving with, okay? It's like if you're in your car and you throw your cell phone for some reason, if you throw anything straight up in the air, well, the car moves out from under it. Probably not really, because it was already moving at the speed that the car is also moving. This might be different if, let's say you're on the BART or in a car and you throw something before it starts moving, you throw something in the air and then it starts moving while it's in the air, that would cause it to fall behind it. But if it's already moving when you throw it, it's going to end up landing on the same base if they're moving in the same direction to start with. So here's our, he lands on Wally. That's your answer. Here's our explanation. And here, so answer, explanation, and evidence. We saw this in the ballistics cart lab. The ballistics cart, I guess it was a demo. When the cart was moving and shot something in the air and shot the ball into the air, the ball landed back in the cart. Landed in the cart. So you see how when I give this evidence, I don't just put the ballistics cart. I have to say why that evidence is worthwhile evidence, okay? So, answer. You have to answer the question. He lands on Wally. The explanation. Why does he land on Wally? Because he was already moving at Wally's speed when he jumped. And so if Wally's still going at that same speed, he'll land back on him. And then evidence. We saw this in the ballistics cart demo. When the cart was moving and shot the ball into the air, the ball landed in the cart again because they were moving at the same speed. If you have a real life example, like I saw this once on the BART, whatever, just make sure you explain it, okay? As long as you can explain your answer, you can usually get credit for it. But if you just put something like the BART, that does not tell us anything. Make sure you explain it, okay? All right. Keep on going while dancing in space. Da-da-da-da. Da-da-da. Ba-ba-ba. Okay, this is a collision problem. We have Wally and Eve dancing in space. They fly into each other's arms. So we have a collision problem. Before the collision, what happens? We have, let's do some different color. This is fine. We have Wally. We have Eva. And they fly into each other's arms. We know that Wally's mass is 40 kilograms. He is moving at 2 meters per second. Here's Wally. Here's Eva. My very detailed drawings. Da-da-da. At a speed of... Her mass is 50 kilograms. And she's moving towards Wally at a velocity of 4 meters per second. That means he's moving this way, she's moving that way, which means one of their velocities has to be negative, okay? Because it's moving in the opposite direction. So I'm going to give her the negative. Okay, so what is their momentum? His momentum, remember momentum is mv. And I like to set up the charts like this, where it's MVP, MVP, because it helps me realize what am I actually looking for in this case. Okay, and it keeps me in track, like makes me realize I have to figure out the momentum before I can move on. Okay, so the momentum is going to be 40 times 2. Sorry, let's make sure we do this correctly. It's going to be 40 kilograms times 2 meters per second, which is going to give you 80 kilogram meters per second. Don't forget your units. Okay, over here, if I do MV, I end up with 50 kilograms times negative 4 meters per second. Okay, so that's going to be negative 200. 200? No. Yes. Is this one right? 80? Yes. Okay, let me make sure. This should be right. Yes, and then 50 times 4. Yep, good. You guys, this is why we have calculators. Okay, kilogram meters per second. It makes sense that she would have a higher, if you ignore the negative, she has more momentum because she is more massive and going faster. All right, cool. So what's our total momentum? Our total momentum before is going to be 80 kilogram meters per second. Can you see this? There we go. Plus that negative 200 kilogram meters per second. So that's going to be negative 120 kilogram meters per second. Okay, awesome. Yep. Cool. Why do I care about this? Because now after that collision, okay, how fast are they moving together? That means this is a sticky collision. This is an inelastic collision. So then after, the system acts as one, okay? So we have the mass is now Wally's 40 kilograms plus Eva's 50 kilograms. But we don't know how fast they're going. But we do know that that momentum is still mass times velocity. And in this case, it's going to be, so this is 90 kilograms. And it's going to be 90 V, okay? 90 kilograms times V. And I'm going to leave that kilograms off for right now. I know that these two things have to be equal. The momentum before has to equal the momentum afterwards. So negative 120 kilogram meters per second has to equal 90 V. Okay, so now I'm going to divide both of them by 90, divide by 90, 120 divided by 90, negative 120 divided by 90 is going to be, my velocity is going to be negative 1.3 repeating, and you can just leave it as 1.3 meters per second. Boom. Hopefully that made sense. You can see again why I like to set this up as a chart. Okay, so the masses are all in line, so I know that if I'm going to add the masses, they have to be these two. I can definitely see what I'm solving for, and I know that my total momentum has to equal my final momentum, and then I can solve for V. Okay, last problem. Da-da-da. Bernie's job is fixing. Da-da-da-da-da-da. Okay. Oh, look, this is a sound problem. He gets trapped outside. Bernie complains by beating his robot arms at the door and screaming. Robot screams. Can the people hear him? Give answer, evidence, explanation, and evidence. No, he's in space. He is in space. And sound does not travel in space. Does not travel in a vacuum, such as space. Such as space, because there are no molecules. No molecules to vibrate and make that wave keep, and how do we say it? The scientific way is to say to propagate the wave, okay? We'll say to move the sound wave. Okay, so there's my answer. Here's my explanation. And then what's my evidence? Okay, so we saw in the lab where we put a cell phone in a vacuum chamber. Vacuum chamber. We couldn't hear it. Okay, because there were no and this was, we found out, because no molecules, because all the air was taken out, to vibrate. Okay, so remember that's the lab where, and you could draw a picture, we had this thing, the cell phone was hanging, we could not hear it, no sound, because we took all the air out, so there's nothing to vibrate. Awesome. Can they hear the knocking? Okay, so can they hear him scream? No. Can they hear him knocking? Yes. If you, let's see, so there's my answer. My explanation. By hitting the door, he vibrates the door, making it resonate, making it and anything connected to it vibrate. Okay, this was, so there's my answer, here's my answer, here's my explanation, and then evidence. There's so much evidence for this, the kind of thing like, when we put the music box on the table, it vibrated the whole table. Vibrated the entire tabletop and got louder. Okay, and that's because of the natural frequency. But really what we care about is the fact that it made the entire table vibrate, and so then you could hear it, okay? So by having something to vibrate, when he hits that door, you could hear it. But by screaming in space, when the air left his face, or whatever little robot apparatus makes sound, it didn't have anything to vibrate, and so then it couldn't propagate that sound. Okay, so remember, these answers need to have answer, explanation, and evidence. So make sure you include all of those things on your test. Make sure you bring your calculator to your test tomorrow or on Wednesday if you're in F block. And good luck. Bye.